Hello, my name is Emily Klavditcher, and I will be talking to you today about the article Turning a Riboflavin-Binding Protein into a Self-Sufficient Monooxygenase by Cofactor Redesign. The article discusses the artificial production of an NADPH-independent monooxygenase enzyme by cofactor redesign. Their goal is to replace the native NADPH with hydrogen peroxide, which is cheaper and more stable. It reduces the flavin and reacts with oxygen in a faster way than NADPH. The self-sufficient NADPH-independent monooxygenases are made by cofactor redesign. A cofactor is bound to protein and is required for biological activity. The N5-alkylated flavins are more stable when hydrogen peroxide is used. Flavoenzymes capable of hydrogen peroxide-driven and antioselective sulfoxidations are created by N-alkylated flavins binding to riboflavin-binding proteins. The N-antioselective dependent flavins are used in oral antimoners. We can alter their flavin structure. Cofactor redesign is viable to create artificial flavoenzymes. The results of how well they performed their experiment are in Table 1 of the article. The monooxygenase enzyme is a special biocatalyst that can be programmed to selectively oxidize substrates. The only problem is that it is dependent on nicotinamide factors that require the very expensive NADPH. Their goal is to achieve self-sufficiency through experimentation. They tested many flavins, cofactors, and riboflavin-binding proteins, which they extracted from chickens. The results are displayed in Table 1. The two columns of Table 1 are titled with R, and it shows the particular cofactors attached to the R subunit. The next column shows which flavin they used. There are 6 different structures that were used in this experiment. Some are displayed in Scheme 2. The next column shows whether a protein is present or absent, and the last 2 columns are the results of the experiment. It displays the conversion percentage of sulfides by the fiber-protein complex and the percent product produced of excess RNS sulfoxides, which measures the antioselectivity. Analyzing the data shows us that flavin structure 2 and 6 produced excess R sulfoxide, while 3 through 5 flavins produced excess S sulfides. Based off this finding, we now know that we can choose which flavin to use for a desired result. A closer look shows that number 14 was the most efficient because it had the most excess. 17 and 19 weren't successful because they were controls, but the rest of the experiment was. My picture shows the R groups right here, R1 and R2, that are discussed in the table, and this is the self-sufficient flavored protein monooxygenase. Here is the riboflavin-binding protein, and here is hydrogen peroxide and the N5-alkylated flavins. Thank you.